All right, it's 5 o'clock somewhere, and that somewhere's here. So it's time for CFRG. I'd like to welcome everybody on behalf of the three chairs, Stanislav, who's online, Alexei, and myself. Hello. So we don't have a slide for the agenda. The agenda was shown in the first meeting, but it's online. We've got a huge selection of talks to go through today, some of which relate to adopted drafts, some relate to new work or interesting ideas. And so just to get going, let's get it started. So here's the first presentation.
Hello, everyone. Hello. Hi, my name is Michele. This talk is going to be about updating the state on the Sigma protocols and Fiat Shamir internet drafts. We're going to try something different, and I'm going to let Vishruti, a recent contributor, give most of the talk.
So for a little bit of background, interactive proofs usually involve two parties, a prover and a verifier. And unlike traditional proofs, you're allowed to have many rounds of messages between the prover and the verifier. So our first draft is the Sigma protocols draft, which is the simplest type of interactive proof. This involves exactly 3 messages between the prover and the verifier. And our second draft is to make the Fiat Shamir transform, which is a way to make any interactive proof non-interactive via replacing the verifier's challenges with a hash function over the transcript of messages so far. So the reason that today we want to talk about Sigma protocols and Fiat Shamir is because we believe that these form fundamental building blocks of a lot more complicated protocols and zero-knowledge proofs. For example, we have rollups, identity verification, anonymous credentials, and signatures, which all rely on some form of Sigma protocols and Fiat Shamir, and we believe that by standardizing these fundamental protocols and starting from a more unified starting point, we can build on top of it and build more complex protocols. So as a reminder for our what we currently have out there, we have the Sigma protocol spec, the interactive Sigma protocol spec, as well as the Fiat Shamir transform spec. We also have the Python and Sage reference implementation, which is meant to follow the Sigma protocols and Fiat Shamir spec as closely as possible, along with the spec-compatible Rust implementation of the Sigma protocols and Fiat Shamir specs, which is meant to extend the functionalities in the Python and Sage implementation, providing extra optimizations. Finally, we also have the spec-compatible Rust Fiat Shamir implementation. So for a bit of an update for what's happened since IETF 123, first we got a security review done by OpenZPL Security. There were no fundamental issues found. It was mostly just editorial changes and polishes, which is very useful feedback for us to polish the spec. Second, we have other specs that are adopting the Sigma protocol and Fiat Shamir specs. For example, there is the ARC spec, which is moving towards adopting the Sigma protocols and Fiat Shamir spec, as well as the ACT spec, which has already adopted the Sigma protocols and Fiat Shamir specs, getting us to a place where other people are able to use and adopt our specs was a very illuminating process because we learned how other people would want to use Sigma protocols and want to see it used in their own specs. So this is a very helpful process in us bringing the spec to a more usable state. So one way to use Sigma protocols is our Sigma protocols and Fiat Shamir spec is by using the NI Sigma protocols class. This is defined by the underlying interactive protocol, the hash function used to instantiate the Fiat Shamir, as well as the codec, which provides a mapping between prover and verifier messages to and from the hash function domain. So the way to use the NI-Sigma protocol class is by instantiating with one of our cipher suites that are defined in the spec. So we currently have 3 cipher suites defined in the spec by concretely specifying the underlying protocol hash and codec. So other specs are also using our cipher suites. For example, we have ARC and ACT that are both using our NI-Sigma protocol class. ARC is, this is a very simplified example of how they're using it, but for example, ARC is using it to do a pretty simple Schnorr proof, proof of knowledge of discrete log, and ACT is using it for proof of knowledge of opening for a Peterson commitment. ARC chose to explicitly define the cipher suite they'd like to use, whereas in the ACT specification, it's more generic with the NI-Sigma protocol, and whoever is implementing on top of it can concretely define a cipher suite on top of it. And while our spec defines a pretty small cipher suite, you can define your own according to your use case by specifying your own underlying protocol hash and codec according to the use case.
And so while the Sigma protocol specification is targeting mostly primordial groups over elliptic curves, these objects are very well defined. And in fact, they are so well defined that there are at least 3 different definitions that appear in the IETF for BBS, for restricted 255, and for hashing into the elliptic curves. And it's challenging for us to build something that builds on top of the 3 of them while maintaining some sort of coherence. And what's even more challenging, and where the problem starts showing up as well, is when you look at the reference implementation. It is common, at least to my understanding, to inherit the Sage boilerplate code from hashing to the curve. And it's not easy to just inherit that, partially because it makes inspection and auditing really hard. That was one of the feedbacks that we got with the audit, that it was really hard to understand even why some primitives that are not needed for building Sigma protocols, like hashing into the group, are in this repository at all, as well as some security concerns. One such example is that point deserialization in hashing to the elliptic curve, or better, field element deserialization, does not validate whether the element is less than the field characteristic, which in the case of Sigma protocols results in a break of soundness. And so what do? Are we going to just change that line and hope that people figure it out? Are we going to do something different? And this is also a question for the community that we don't really know how to solve. Our approach here is currently, or has currently been, to build a Python package that provides a clean group primitive that adopters can reuse, essentially by means of Python packaging, and iterate over a little bit faster as we talk to the adopters. This code is not meant for deployment. It's still just meant to provide a reference implementation, but potentially can be easier to build on top from. And honestly, this is more work for adopters in the community that we're doing more than for the Sigma protocol specification itself. So also here, feedback and help from the community would be very much welcome. And we kind of want to avoid a situation where, we build yet another group definition. And so the question is can we get all together and be a nice family and build something? Specifically also, I'm saying this as a result of the pairing-friendly curve discussion, where potentially we can do a little surgery there and try to come to an agreement. And speaking of next steps, I'll pass it over to Shruti again for some open questions.
So first, we already started a formal verification process of the spec. We want to be as legitimate as widely used internet standards like TLS. And so we'd love help from the community to contribute to this effort of formally verifying our spec. Next, we would always want to know how you would like to use Sigma protocols and Fiat Shamir. We want to continue hearing about different use cases and always want to point you back to the Rust implementation for extra examples for how you can extend and optimize the Sigma protocol spec. Finally, we just want to wrap it up by saying that we have 2 specs, the interactive Sigma protocol spec, as well as the Fiat Shamir spec. And thank you for taking your time to listen to us today. And yeah, please ask any questions that you have.
Hi, I'm Deirdre. Excited to see this progressing. For hash to curve, and I support implementing yet another implementation in Sage or Python for your version of a prime order. I'm assuming it's a prime order group. Okay, with the hashing to the group explicitly defined and the niceness of the group elements and field elements and all that. Are you writing that down in your documents, not just having another? Or are in your documents, are you saying you must have a prime order group and a hash to curve solution and a mapping to the finite field or for the group elements over a finite field that meets these criteria? So, because I can see myself wanting to use like Ristretto, and Ristretto already has its own hash to curve solution. If that's going to skew from what you define in your documents, I would like to be able to figure out if that's allowable skew, if it's not that defined in the document, so it's okay. But if it is going to be defined, your new thing is going to be defined in the documents, have to figure out if it's okay to use the original Ristretto one or not, that sort of thing.
For now, in the specification itself is a mixture of things that were stitched together from hash to curve and BBS. With some workarounds, for instance, for the issue that I mentioned, as well for hashing to the curve, there is a definition of an elliptic curve group that can also serialize field elements. And it is hard for us to standardize via Shamir in a way that can also be used with things that are not elliptic curve groups. And so we sort of split it up in a way that should work together with all of these things. My concern is mostly like how precise, and the things that I don't know from experience is like how precise does this interface need to be within a specification. Receptors seem very liberal in the way that you implement these things. So I'm mostly concerned about how precise the interface in the spec needs to be while avoiding some problems and making clear what are the guarantees that need to be done.
Hey, hello. Yeah, so there was a massive effort on the hash to curve draft to get the group's situation aligned with all different curves, at least with the most important curves. So I think it would be great to just rely on that work, and yeah, because it also the BOPRF draft defines all the serialization, and it would be good to rely on that thing because it's already done, and we have investigated about that.
Yeah, right now,
regarding
what I'm doing right now is essentially like copying exactly what what was done there, stripping out the field serialization primitive into like something that just belonged to field elements and just relying on the same serialization tools that your guys are using.
Yeah, the problem that changing serialization is you change everything. Even though the objects are the same, changing just the serialization format is it's gonna mess us.
No, I'm not going to change that, but I'm going to change how you validate that.
Oh yeah, sure. Validation is good. Also happy to contribute with the software Python implementation.
Nice, thanks.
Chris Patton, Cloudflare. Oh, okay. So I would, yeah. So there like there's a lot of like slightly different APIs for prime order groups that we've been kicking around. I would say just go with what works for you, and whatever like the API, just like do whatever works for your draft. We want to make sure that things are wire compatible with what's already been deployed. So hash to curve from the hash to curve draft for like P256 should interoperate with this draft. And if you need to be stricter, like point out where we're stricter and why. That's really, really useful. I think that's all I had. Thanks.
Okay, we locked the queue. Thanks very much. Chris, I believe you had another last minute agenda bash. Chris Wood is having somebody else present. And it's Yella who's presenting remotely. Thank you.
All right. Can you hear me?
Yep.
Perfect. Thank you. Yeah, this is my first time at IETF, so thank you very much for having me. Yep, I'm presenting also on behalf of Chris, who is probably in the audience somewhere, and also we made this draft with Stanislav Jarecki. Yeah, so I wanted to give a few updates on the spec and some work we plan to do in the future. So very quickly to recap, this is about password authenticated key exchanges. And I want to explain why you want to have such a password authenticated key exchange. So the use case we're thinking of is, for example, there is some kind of vault and I want to get the contents of my vault remotely from an operator. Well, they can send it in plain text, but then anyone can see what's in my vault. So we should probably encrypt it, and we can do some kind of key exchange to set up an encrypted channel. Unfortunately, if there's no, there's no authentication in this case, so they don't know who they are sending this data to. If we want authentication and there's no public key infrastructure, then a password authenticated key exchange would work, where both of us know a password, and we can only set up a channel if we actually both share the same password. Unfortunately, this is called opaque. Unfortunately, because both of us know the password, the vault operator can impersonate the user. So instead, we want some kind of asymmetric opaque, which is called an opaque. In that case, the user has a password, and the vault operator only has a verifier with which they cannot easily impersonate the user. So this is great, but we are proposing post-quantum opaques. And the reason we want to do so is that classical opaques suffer from some issues when quantum computers come around. Specifically, a quantum computer may attack the encrypted data that has been sent to the secure channel. They can break it even after observing the transaction and getting access to a quantum computer at some later time. Or looking at a transaction, they might even be able to attack the password, so to extract the password that was used in a previous session. A post-quantum opaque prevents these kind of attacks. Now, in our proposal, we are actually proposing a hybrid opaque. And a hybrid can be seen as a combination of a classical and a post-quantum solution. And the reason we want to do something like that is that a hybrid approach is at least as strong as the classical approach. So instead of completely replacing the classical approach, we are adding something to it. Well, how to design a hybrid opaque? So I said you combine something classical with something post-quantum, and that's what we did in this case as well. So we have two closed box protocols, and we have some kind of wrapper around them to make one giant hybrid opaque or opaque. So the way we achieve an opaque is we take what was on the previous slide and we build even more mechanics around it. Now, one question I would like to get some feedback on is whether we should be standardizing a post-quantum opaque or a hybrid opaque or both. Well, we have gone for the hybrid opaque path, but so far that means that the document only contains a post-quantum regular opaque and a hybrid opaque. This hybrid opaque is called CPACE opaque plus. What we could do is take the same transformation that we use to go from CPACE opaque to CPACE opaque plus to achieve also a post-quantum opaque, so one that is purely post-quantum. We could call it opaque plus. I want to talk you over what the actual differences are in properties that these proposals like these protocols would achieve. So Oakwake Plus would not be at least as strong as CPACE. It's a completely different kind of take, while CPACE Oakwake Plus definitely achieves this. However, when you look at efficiency, it is more efficient than a hybrid APAC because we need to do less rounds. The bandwidth is roughly the same. So what we get is there is some kind of trade-off between security and efficiency. So we are wondering if there are some cases where we are okay with sacrificing some efficiency in order to get some more security, or the other way around. Now, something completely different. Since we made this spec, we found out about some possible timing side channels in Oakwake, and Oakwake being the post-quantum bake component. So Oakwake is this protocol between two parties who both know the password. And this is what it looks like in a nutshell, but really it suffices to look only at the first part. So this first part suffers from a very particular timing side channel in that if you know the public key that is being generated, like the CAM public key, then you can perform offline password guessing. And it turns out the way we specify things, we don't actually say that you need to protect this public key generation against timing side channels. Now, the MLChem spec, so the FIPS specification of MLChem also does not require generating the public key in constant time. So this at least leaves the option for such timing side channels to exist. So there are two ways we can go about addressing these timing side channels in our proposal. One is to actually require MLChem to be completely done in constant time, like MLChem key generation, which is the easiest to specify, but not necessarily the best option to choose. Another option is to introduce changes to the protocol, and those specific changes are called tempo, and I'll refer to it later as well. So comparing the properties of both approaches, the first approach, it requires very little changes to the spec. Fortunately, tempo also requires a small amount of changes, but more than just saying that the MLChem needs to be implemented in constant time. However, if we have to do key generation completely in constant time, it will become significantly slower. And the tempo solution is better in that regard because the performance impact is really small. Finally, the problem is if we just say that MLChem needs to be implemented in constant time, it means that people cannot just use a FIPS compliant implementation of MLChem. They really need to have special implementations that are particularly geared towards this protocol. The nice thing about the changes in tempo are that we can build a little wrapper around FIPS compliant MLChems, and that will allow anyone to use like a closed box solution. So very quickly, the reason there is this kind of timing side channel in MLChem, by the way, it's not really a timing side channel in that it's a vulnerability in MLChem. It's just that we need very strong properties that the MLChem spec doesn't specify. So the way that this part of keygen works is that we start with some kind of compact public key and we expand it into a full public key. Specifically, the seed is expanded. And in expanding the seed, there's a lot of rejection sampling happening. Turns out that the number of rejections that happen leak information about this 256-bit random seed. And if you can work out this seed, you can perform this offline password guessing attack that we were talking about before. So this simple fix called tempo works as follows. Before, we had this line where we said encrypt. It's not really an encryption, but it's similar, where we encrypt with the password the compact public key generated by MLChem. The solution is to take out the seed from this compact public key and not encrypt it at all. Just send it in plain text to the other side. This works because the seed is completely random. And the matrices, the other part of the compact public key, are generated without rejection sampling. So this has been documented in full detail in this paper. Since then, we've also made some other changes to the spec. So Chris Wood made some changes to the introduction and the motivation for the use of a hybrid bake. Dan Harkins noticed an inconsistency between one of the papers and the specification, so that the paper that the specification is based on. So we fixed that. And then Stanislav Jarecki also came up with some fixes that we have yet to apply, but are still working on. In conclusion, there are two questions that could be discussed in more detail. One is, should we focus on a hybrid APEC, or should we also offer a post-quantum APEC? Then, is tempo really the right approach to protect Oak-Quake against timing side channels? And finally, the next steps for us are to submit a revised version, and we plan to do so before IETF 125. And the plan is to incorporate the changes laid out in tempo, unless there are any concerns with that, and to address all the current open issues that you can find in this GitHub repository. Thank you.
Chris Patton again. I think I would focus on a pure post-quantum APEC. I don't really believe in hybrid for this particular use case. Just in general, if we have to eat a lot of cost to make something hybrid, especially when it's like fancy crypto, quote unquote, I don't think it's worth doing. In this particular case, though, I wonder if you guys are approaching the problem in the right way. I'd like to understand. So I get the motivation of, I have a generic protocol CPACE, I have a generic protocol Oak-Quake, and I want to mash them together without breaking abstraction boundaries. But I think this might be a time where I wonder how good you can do if you did break the abstraction boundary. So five messages is just too many, I think, in my opinion. You might have a use case for it, but I can't imagine deploying that. So I'd be curious to see where we can go if you're take MLChem, take an OPRF, stick them together and make something new. To the second question, yeah, the tempo fix makes the most sense. I think you guys are spot on there. Thanks.
I think it's a fair comment, but remember that these kind of fakes are used in a situation where the user typically has to type in a password. So like, these are situations where you might be able to get away with a couple more interactions. But I do agree also that the cost is pretty high as compared to, for example, a hybrid key exchange.
Dennis Jackson, Mozilla. Thank you for the really nice presentation. I think I would back Chris on doing a pure post-quantum PAKE rather than a hybrid, simply because, as you illustrated in this talk, you've got this low entropy secret. It's going to be sticking around, and you really, really care about side channels. So feeding it through twice as many things is more attack surface for that kind of issue.
Right, but in the specification, in the second PAKE, it's actually not really the password that we put in. It's essentially the secret, like the session key generated by the first PAKE.
Oh, that's kind of fun. Okay, that's neat. But more widely, it's also not obvious why you sort of want this kind of really long-term property, because it's a low entropy secret at the end of the day. So keeping it around for the time that we have a quantum computer doesn't seem like super great.
So maybe, since I'm not a PAKE expert, maybe you could restate the properties of the, in this case, if it is a pure, if we do the pure post-quantum one, is the property the password leaks or the traffic key leaks?
No, so it should protect against both.
The hypothetical where like MLChem is broken, like does the traffic key leak?
In this specific case, for Oak-Quake, you would be able to extract both the password and the encrypted contents.
Right, so that would be unfortunate, I think. So like I don't have a position. I tend to agree with you, like the performance in terms of like number of milliseconds and bytes exchanged is not a big deal in the context of opaque, because as you say, it is an interactive process. However, the number of round trips is a serious problem, not for performance, but as we discussed in TLS, for protocol bindings. And so if you're stuck with a situation where you have like a 5-message exchange, then you have a real problem with protocol bindings. So I think that would be like, I think the more serious issue than like how many bytes have to go back and forth, or how many milliseconds it takes.
Right, I completely agree. I think for TLS, we might be able to look at a more specific kind of bake that fits in 3 rounds. I think that might be a better approach. See what we can do there.
Hi, I'm Deirdre. I echo what Chris Patton said and what Ecker said. I did a quick grep. You don't explain why you use the sequential combiner over the parallel combiner. You say that it is obviously better, but not why. It seems like it's possible you could get this from 5 rounds into 3 rounds. If you did the parallel combiner, maybe I misunderstand, but if you could explain why not the parallel combiner?
I think this is a misunderstanding. We are not aware of any post-quantum bakes that you can make from standardized primitives that you can actually use in the parallel combiner, because you need a very strong property that is not satisfied by Oakwake. And there is actually one recent solution, but that one is like the bandwidth is significantly larger for that bake, and it's very non-standard.
Okay, thank you. If we could put something in the draft, because I think if you literally just say there is no good PQ version that will satisfy the parallel, so we need to do sequential, that'll make me happy.
Very good point.
Echoing what we just said, that more bytes, more communication is not really an issue. Fitting it into other protocols is definitely an issue. I have done a lot of threshold work, and I don't think there's a notion in Pake land for robustness of a protocol, of literally like, how likely are you going to finish the protocol, given how many, bad things happen? Kind of in the threshold world, you might have, T of N or need to be good and honest and doing the protocol correctly to finish the protocol with some amount of probability. We only have 2 people, but basically more rounds, more possibility of something going wrong, more possibility of just the protocol not succeeding. If it's the PQ version, not the hybrid version, it's shorter and more likely to succeed. So I like the PQ version. That's it. Thank you.
Fair point. Thanks.
Okay. Jumping on the bandwagon, I agree with what Eckert and Deidre said about messages. Pakes only make sense in existing and in the context of a larger protocol to actually use the keys to actually do something. For existing protocols, trying to shove in a 5-round protocol sub-protocol doesn't work. We really need to minimize it, even if the time cost is irrelevant.
Thank you.
All right, thank you.
All right, so Abhi has done a last-minute change, and Tim is going to be doing the presentation.
Thank you. Right, so as Nick just explained, I'm in the slightly awkward position of presenting somebody else's slides, although Abhi's with us remotely, so any particularly difficult questions, I'm going to refer over to him. Okay, so we're here to talk about Longfellow, which has been talked about a fair bit this week. And yeah, I'm presenting here on behalf of Abhi and Matteo, who are really the inventors of this whole scheme. Next slide, please.
Hold on one second.
No rush.
I'll give you the clicker, yes? Try.
Yep. All right, so problem statement. What is this for? Right, so what we want is zero knowledge schemes for small identity theorems. So what we have here on slides is 2 excerpts, but one on the left from the architecture reference framework for the European Union Digital Identity Wallet. So what this calls out is, I don't think this is a requirement, but like a suggestion that, we could use zero knowledge proofs as a mechanism for users to authenticate to relying parties. On the right-hand side, Specifically, there's reference to like this work from some EU publications on how to address, yep, that specifically says technical specifications for age verification, which is the very sensitive problem here, right? That's being discussed so much in a lot of venues, so much so I see Martin probably a little tired of hearing those two words together by this point. But for those who don't know, the idea is many websites are beginning to require users to prove that they're, say, over 18 before they will serve you adult content or that they will let you use social media. Okay, then further, there are venues here at IETF that are expressing growing interest in zero-knowledge schemes. So up at OAuth, they're working on selective disclosure JOTs. And the idea is that selective disclosure is cool, but you still relieve the thing that you selected to disclose. And so it'd be awesome if you could instead prove in zero knowledge the particular claim. And of course, we want zero knowledge schemes that are post-quantum. So we don't want to deploy new ECC-based stuff. The nuance I suppose I should call out here, especially in the context of Longfellow, is that the proof system is post-quantum. But of course, you're proving statements from a credential that was signed with P256. So naturally, an adversary who has a CRQC could forge the underlying credential and then emit proofs from that. But the point is that the proof system is post-quantum. Okay, so then the other thing that has gotten a lot of traction in this area is the BBS family of signatures. But the particular issue there is legacy support, right? We have many, many credentials already out there, people's passports, people's driver's licenses that contain a P256 signed credential, and compatibility with that is a key goal here. So hopefully all that sort of motivates. We do have, there is a need to have post-quantum zero knowledge schemes that fit these applications. And the question is, where is that work going to happen? Actually, I notice now this slide audaciously suggests that the CFRG is part of the IETF, which is of course inaccurate. But nonetheless, CFRG, you know, it's a place that comes to mind and appears in many conversations, possibly a place to do this. Oh, sorry. Oh, sorry. I thought I heard a little somebody in the queue noise. All right. So this work did get presented at CFRG at IETF 123. So what's new since then? So in particular, so yeah, first off, there's growing interest from, I suppose when this says external, that refers to, you know, Google. It's from the perspective of the authors of the slide. So we at ISRG have been working on a second implementation of this. This is a second relative to the first implementation, which is a C++ implementation of Longfellow that the Googlers put up on GitHub. So right, we've been doing a second implementation in Rust. It's linked there on the slide. So the motivation here is, you know, more implementations, more better, and it's helped us flush out like a ton of issues in the draft spec so far. We've written up 42 of them at the moment, and they're all up on GitHub. We're also interested in eventually working on a Sage reference implementation. Sage and or Python, like we want to take some of what we learned working on VDAF. You know, what we like is the notion of being able to reconstruct test vectors automatically from the code, and having like the sort of code snippets that are in the spec be excerpts from the actual implementation, because then we can verify that it's correct, as opposed to it being some sort of like weird handwritten pseudocode that's like Fortran-ish or whatever. Right, so we're working on this, and then there are a few different EUDI wallet implementations out there that either have integrated this, Multipass, I believe, has pulled in the C++ stuff, and WW Wallet by the Ceros Foundation wants to pull this in as sort of one of their mechanisms for authentication. There have been a couple of security reviews done on this work. Trail of Bits did a study, which they published, and is, yeah, I believe you can find a PDF of their all their results up on GitHub. And then Lejero took a look at this. The report has not yet been published, though it's coming. Neither, you know, there were findings, but neither one found any issues with respect to the zero knowledge scheme. Okay, also since the last draft, there's been a lot of performance work done, since, you know, performance is really sort of the killer feature of this whole system. So, and in particular, according to this slide, big improvements in the Reed-Solomon encoding and the sum check prover. There we go. Okay, here's some benchmarks for proof of possession of ECDSA signatures. So, right, we see that the prover side, which would be like on somebody's device, running in 16 to 38 milliseconds, and the verifier side comfortably under 10 to 25 milliseconds. I'll admit I'm not actually sure what the number in the third column actually represents. Abhi, I don't know if you want to jump in and explain what that figure is.
Oh, it's just an artifact. It's the number of iterations of the benchmark test.
Got it. Okay.
Statistically relevant, significant.
So, right, there you go. So that's Longfellow. Then the question would be what to do with this work. So also most recent developments on Monday morning, this got presented at Sec Dispatch. And since then there's been, a variety of discussions going on sort of in the hallways here at IETF of what to do with this. So maybe something working group flavored will emerge on the engineering side. But I suppose what's of concern for this room and this session is what might CFRG want to do with it? And then, yep, backup slides.
I have a lot of opinions today. I'm sorry, everybody. So I had a couple questions about the PQ of it all. So Longfellow, the proof system is PQ. Is the idea that proving statements about ECDSA signatures is also PQ? That is Longfellow itself, PQ private. Is Longfellow itself PQ private? As in you get zero knowledge even if there's a quantum attacker?
I think that's right. Abhi, do you want to comment?
Yes. And
Great.
I think the point we're trying to make is that, and we haven't done this yet, but we're working on an MLChem. We're working on the same sort of thing for something like MLChem. So that's more the point, which is that if you pair this with the PQ signature, then the whole system would gracefully upgrade to that.
Got it. That's neat. What do we actually have to prove? Is zero knowledge statistical or information theoretical, or what is it reduced to?
That's a pretty tricky question that I can't answer on this thing. There's the interactive version of it for which we can prove the statistical ZK in a query bounded model. So that's a pretty, I can't give a precise 30-second version of that, but there are two aspects, the interactive security, and then after you apply fiat Shamir, what that becomes. And the Ligero report actually is going to have a pretty long discussion about that.
Cool.
We can actually achieve what's called statistical witness indistinguishability in the unbounded query model, et cetera, which is a strong privacy property that this system can achieve.
That's great news. One comment on the potential of swapping ECDSA for MLDSA. My concern when I think about that is MLDSA is quite a bit more, did I say MLChem? No, I said MLDSA.
I said Chem, I'm sorry, I made the mistake.
No problem. MLDSA is quite a bit more complicated than ECDSA. So the proof would be a lot bigger. I've been kind of thinking about this problem this summer. I don't have any definitive answers, but my impression is that this is probably not the right direction to go in for building fully PQ anonymous credentials or anything else. I mean, maybe you can do it and it's worth looking at, but MLDSA, look at MLDSA now and start to think about if you think you could actually make it work, because
we are working on MLDSA 44. I think that's the version that we're looking at, and
that's good enough.
That's exactly the question we're trying to answer: is how big would the proof be? Which is we can estimate, but we're trying to find the exact number. It's not a complicated scheme to verify. Remember, all you need to do is implement the.
Yeah, that's true. That's true.
So yeah, that's a data point we'll have, and I agree with you that in fact it could be the case that a more direct signature scheme that has implicit proof of possession, like an optimized proof of possession, could be relevant there.
Cool. Yeah, it would be great to see those numbers at the next IETF. Thanks.
Hi, Eric Scorla. I mean, this is super cool. You're gonna feel like I'm jerking you around after I said that.
Just checking who's in queue.
Yeah. So I mean, like this is super cool. The problem statement that I have for this, as I think that you quite clearly say, is we have these existing credentials that were encrypted, that were assigned with some specific thing. We want to keep using them, right? And so to the extent to which we think that future post-quantum credentials will be assigned with MLDSA, then the problem remains the same unless we can persuade them to use some other signature algorithm. I mean, the general situation is we have like zero leverage with the people making these credentials. And so they're just going to use whatever they use. And almost certainly going to cross out like ECDSA and write MLDSA. And like, we'd be lucky if we got them across, like write BBS in there. I don't think that's actually very likely. So I think that like this kind of generic zero knowledge proof system that like can cover any potential signature scheme is like, is probably a good way to go. I actually like, those performance numbers are like so good now that I really don't care. You know, I mean, bear in mind that for H assurance, like the alternatives are that you take a selfie, or that you, you know, that you hold, you know, you hold your ID up to the camera. And so like you're already transmitting like megabits of data and taking seconds. And so like if the whole thing operation took like a second and a half on your phone, like and transmitted a megabyte of data, I really would not care. So and it's similar, it doesn't really matter if like it consumes a second on the verifier side, because it doesn't have to happen very often. And so like these numbers are already good enough. So make it better by all means, but like I don't really care. So congratulations. Now's the part where I'm going to feel like I'm jerking you around. I believe that the CFRG should focus its attention on vetting and designing primitives which are of use to IETF protocols. And while it may be the case in the future that there's an IETF protocol which is to make use of this, there is not one now. And until that point, I think this should probably be tabled. Although I'd be happy to see more presentations, but like I think the CFRG should not be like working to write an RFC on this document until an IETF protocol demands it. At the point where an IETF protocol demands it, I'm not like unenthusiastic about the concept, and I think we may very well have a protocol that demands it, but I think until that point, it's probably not worth the CFRG's like main focus of attention. But I don't want you to take this as like a lack of enthusiasm for the scheme. I'm merely trying to focus our attention on the things that service the IETF needs.
Yeah,
So I appreciate that feedback. One point of reference there is that in the past, it has been the case like opaque and many other versions are things that haven't been referred to but have been predicted to be useful. Opaque was the best example of that. And some of the other things, even in these sessions, I think we could make the same criticism for. And the SDJOT community did, in fact, Brian Campbell and those people did, in fact, ask for this kind of thing. So
I guess let me hit those in turn. The SDJOT thing does change my opinion. I would like to go read that mailing list, but that would be certainly a good reason to do this. I think that I fear that the opaque argument cuts in the opposite direction. Namely, I think that we did a bunch of spec stuff on the speculative work on the hope that people were going to want to use those systems, and it didn't work out as like we hoped. And so I think like I think that maybe that's true, maybe it's not. But like the SDJOT thing, certainly I think you know, is potentially compelling. So again, I'm really not against this. I just want to make sure that we focus our attention on something which the IETF will make use of eventually.
I have closed the queue. There are already 3 people in there. Stefan, if it's quick, you have a minute and 15 seconds.
Oh, yeah, very short. So I heard Longfellow mentioned in several situations and meetings with the name complex or the word complex. And also with discussions with Abhi here, we sort of concluded that especially used with SDJOT or MDoc, it can be very complex, and it's very dependent on how you form the inputs to the Longfellow. And maybe there's work to be done also in that area to explain how you should formulate the input in order to create less complex circuits. Is that something that is included here or should be co-located with this work?
It's a deep question. I don't have a comment. Tim?
It's a tricky one to answer because like now you're getting to the nuts and bolts of a message that goes over the network. And I honestly don't know if that's the sort of thing CFRG likes to spell out.
It seems like the specific ZK system that in this case is using Ligero could be in theory swappable for a different system. So if wherever this gets adopted, it seems like there can be work to take Longfellow writ large and make that a bit more abstracted as a protocol. And you can say, I need a ZK proof system that has fulfills these properties, and the credential underneath is proving things about must have these properties. It seems like we have some room to make it nicely pluggable for MLDSA or a different, more efficient, better, or whatever ZK proof system in the future that hopefully will still be BQ. I would like to see this turned into something somewhere so that we could work on things like that.
Yeah, I personally like that approach. I think it aligns with a lot of the stuff that Michele has been trying to do for a while. And it does seem to give like a nice path to PQ in particular, right?
Okay, thanks, Tim.
Thanks, everybody. Ooh, thank you, everybody.
So Scott.
Okay.
Sorry.
Um,
MLChem security considerations.
Yeah. Okay, I'll try to make this, give you some time back. Talking about security considerations, basic. Oh, yes. Basically trying to explain what MLChem security goals are, how it meets those, what you need to do to meet those goals. The intended audiences was protocol designers, and eventually went to protocol implementers because I felt like I had to say, use good entropy. I could not say that, but that's really implementer audience, not designer audience. And the whole point is that this should be for this audience boring. Almost everyone should agree with everything that's in this draft. Just that this is intended for the rest of the IETF who has less knowledge. Basically, a general discussion of what MLChem is, how to use it, and 2 sections of security considerations, stuff we can apply to essentially any chem, and some things which are specific to MLChem directly. And again, it's supposed to be pretty boring from a CFRG standpoint. And why are we talking about it? Implementers need to know, protocol designers need to know, and there's also no reason for every single RFC out there which mentions MLChem needs to repeat this. And I found an internet draft which refers to it. I had thought there were more. I searched and only found one. My ask, which I will post on the mailing list, is can we have research group adoption after I do the last updates, which I have not yet done. Daniel, DKG.
Yeah, thanks. Thanks, Scott, for working on this. I would also love to see this document. I don't know that I have much good direct input, but just even the discussion earlier in this session about the constant time properties of keygen for MLChem makes me realize that maybe there's a bunch of things I have no idea to be wary of. Would you put this constant time keygen consideration into this document?
Be honest, until today, I had not considered it. I can certainly consider adding it, although, be honest, MLChem key generation is largely either non-constant time or rather expensive. The previous draft gets around it by exposing the seed, which tells you what is the, actually, no, that's right. Yeah, I'll need to think it through because the non-constant parts are known by leaking if you know the public key. So yeah, I need to think it through. Thank you. But thank you. Daniel?
The Kyber certs draft references this, the CMS Kyber draft references this, and I have an issue for the composite chems to reference this as well. So there's 3 drafts already.
Oh, okay, great.
We'll be
I just,
so
yeah,
please adopt.
Okay, thank you.
Small comment. I've read this draft yesterday, and in decaps section, you say that it does encapsulate. There is encapsulation in the.
You found a typo?
No, that's not a typo. It's a mistake. It does encryption. not encapsulation.
Okay, yeah, it's typo. I'm always surprised
But-
at how many typos I can fit into a short text.
Yeah, but my comment is I find this text sometimes in places a bit too strict. So, for example, in this decap section, the point of this encryption is to compare the ciphertext, but it doesn't mean you have to do the encryption, right? You can do it a different way.
Okay,
So-
if you have alternative text, you can always open up the pull a branch on GitHub and make your suggestions.
All right, I'll do that.
Chris?
That was Chris. Yep.
Oh, I'm
Queue's
sorry.
closed.
Mhm.
Thanks, Scott. Okay, Deirdre, you have the floor.
Cool. All right, this is an update from myself and Richard Barnes on the hybrid chem stuff. Okay, so reviewing what we were tasked with, what we've done since 123 and since our interim in September, which went very nicely. An update on the up-to-date security analysis that we've been doing, and the wrap-up and last-minute feedback. So this is what we were tasked with, to identify which chem security properties are relevant to the IETF, give an overview, provide a small overview of techniques to produce hybrid chems, and then provide 3 concrete hybrid chems using those techniques that fulfill those security properties, specifically 3 with a combination of P56 and MLChem 768, X25519 and MLChem 768, and P384 and MLChem 1024. We have done this. We provide guidance that lets hopefully non-deep in the weeds cryptographers to produce these constructions, these hybrid chems, provide some targets for everybody to try and point at. And we have been doing our damnedest to stay aligned with work in LAMPS, in OpenPGP, in HBKE, and other places around the world, literally. And we think we have done that. So this is the generic document. This is the document that lays out 4 generic frameworks of how to create hybrid chems. We have what we call UK now for universal based on chems. This used to be called GHP in the long history of these documents. We have CG. This used to be called QSF. This is the framework that is used in X-Wing and anything that's X-Wing-like. We have the new UG combiner and the new CK combiner, and I'll go into depth in there in 2 seconds. We removed the pre-hash combiner, which was related to ChemPat. That was out of the interim. There was not a lot of support for that. We tidied up how we want to write all of this stuff because there's some commonalities and we didn't want to be too duplicative. We wanted to kind of be succinct without, without obscuring too much abstraction. We wrote down a default keygen for all of these frameworks that is based on a single seed. I think it's a 32-byte seed. While saying that when you write down your specific concrete hybrid chem instance with specific components and hash functions and all of that stuff, you may deviate from the seed-based keygen with a lot of language in there to be like, with great power comes responsibilities. Here are some of the possible security repercussions if you choose to do that. We did this specifically because the seed-based keygen is a very nice default if you can do it, but there are some settings where you may have a credential that's in hardware and you may have another side of your hybrid chem that's in software, and you just cannot do a single seed based on that sort of environment. You have to have keygen from one side that is controlled by that side and keygen from another side that's more controlled by you. And we allow this. We don't encourage it, but it is allowed according to these documents. We've also added an IANA registry. This has helped us to avoid stepping on each other's toes with the domain separation labels that I'll talk about a little bit more in the future. Fleshed out some binding property proofs in the documents for all of these frameworks. And we have in CCA proofs for the UG, that's a typo, and CK frameworks. The CK1, nope, the UG1 is basically ready to be published on ePrint. The CK1 needs a little bit more work, and we both plan for those to go to ePrint and then link to them from this document. These are very similar proofs to kind of the X-Wing style proofs. We have a proof for what happens if the post-quantum side no longer gives you in CCA and you only rely on the traditional side. And then we do the other side. We do the proof if all you have is the security of the post-quantum component and you don't get any security from the traditional component. So we actually have 4 in CCA proofs for the 2 new frameworks. So this is we've shown this slide before. We have these 4 frameworks where on the left side, the left column, we have no assumption about the post-quantum chem component, except that it gives you in CCA security. And then we give you a construction that directly depends on the group structure, or we give you of the traditional side, or if the traditional side is a chem, it directly relies on the in CCA security of the traditional chem. And then on the other side is if your post-quantum chem also has C2PRI security, so that's ciphertext second pre-image resistance, like the X-Wing style, you can have your traditional component be a group. This is the X-Wing style, or it can be a chem. So that is the one that was inspired by work in LAMPS, where they really wanted to do X-Wing style, but with RSA. And we said, you don't have a proof for that. And so we wrote a proof for that. So that's what that is. And then on the other side, the traditional one with no C2PRI with the group, that's like, pretend you want to do the more conservative combiner without relying on C2PRI, but you don't want to like wrap up your elliptic curve in a DH chem style thing. We went directly to the SDH security of the group to allow you to do that. So that's where that came from. So our new IANA registry registers hybrid chem labels so that if, for example, you wanted to do MLChem 768 and P256 and a different KDF like TurboShake, which is now an RFC, you can do that, but we're going to ask you to register it over here with a different label than another one that also has very similar stuff, just so that they are nicely separated and you don't accidentally create things that don't interoperate well, or people think are similar and mix and matching in the wrong way. First come, first serve policy. So, and then this is the other document. This is the concrete hybrid chems document where we have written down those 3 concrete instances. We align the names of the schemes with the doc. We have the labels and IANA registrations for them. We did a fix for how you're doing scalar, how you're doing generating random scalars for these NIST curves. I think we had the wide reduction before and that was bad, and now we fixed it and we have it in a very particular way for P56 and P384. So that's unbiased and it's short and it's always determined to end in an exact amount of time. It's not running forever and ever and ever. I think it's like we have 3 exact loops for P56 and I forget what the number of loops is for P384. Yes, exactly. We wrote down exactly what you need to do, which is have fixed lengths and fixed sizes for every input to your HKDF usage if you want to use it. And then we updated all of our test vectors in our reference implementation over and over and over again. And that was mostly Richard doing all of that. Okay, the last thing that came up is because we kept adding things and removing things and changing the names and changing things around, because we kept changing the names of the schemes because we kept adding them and moving them around. And we had encoded the name of the framework and the ingredients and all of that into the label that was going inside the actual KDF itself. It kept changing the test vectors every time we just kept changing some name. And it was quite long because I made a dumb decision very early on in these drafts over a year ago to encode all of this information into the label because that's an easy way to make all of the labels different between every set of parameters into each concrete instance. It was very long and it kept changing. People asked us to make it shorter. We were having a very hard time trying to figure out how to just make it shorter without making it unintelligible and hard to understand what it was versus another one. And people asked us to like stop making it dependent on names, semantic names in a document that didn't really change anything in like they kept forcing interop issues and regeneration of test vectors without really changing anything about the security properties. It was just, you know, changing something from being called QSF to calling it CG or something like that. So we chose some labels that were, except for the X-Wing label, the parameter set that's equivalent to X-Wing, to be X-Wing like because it was short and independent of names. And for all the people who were operating on trying to make these things shippable and agreeable, everyone was happy with that, and we merged that. And then other people noticed, and they were very unhappy about that. So we, the authors, ran a poll that had a lot of, you know, IETF people in it, and that showed support for semantic labels again. And the semantic labels again had to be short and not, you know, going to change very much. So the thing that is now on data tracker is this, and the thing that's actually on data tracker has the hex encoding of these labels actually in the document. The X-Wing label has stayed the same because everyone and their mother said, please, please, please don't change the X-Wing label. But the other two, I had to check. Yeah. And the other two are, as you see, MLChem 768-P256, MLChem 1024-B384, and those are, I don't think they're registered yet because we're asking for the IANA registry, but that's what's in our document. The composite chems draft in LAMPS has been updated. I don't know if they pushed a data tracker, but yes, excellent, they have. And we have confirmed interop between all of these things, and everyone seems pretty happy. Reactions, questions, rending of garments, gnashing of teeth. Oh, okay. Okay. Yes.
First, thank you for the RSA proof. We needed it. Second, the IANA registry was new to me, and I wonder if we at LAMPS, I'm not an author, but I'm heavily involved, have to do something about this as well. Do we also have to add our labels to this registry? Because we're doing very similar stuff.
Yeah, that's a good question.
I would say you don't, as Richard Barnes, you don't have to, but you probably should. Okay. It'll be 5 lines in the draft.
Yeah.
So it's not a must, it's a should. But we will.
Yeah, I will comment that having an IANA registry in IRTF research document is rare, but for things that are protocol shaped, like HPKE, we've done it. So
right.
I would, yeah, I think this is probably fine. And if anyone has any ideas or history on this IANA, you know, from a aesthetic perspective, please share that. Please share it. But I think we're probably just going to go with this.
Cool. Yes.
Rowan May, I'm happy with where we are now.
Yes.
And I would just say that please keep implementers in mind when you come up with names, because like having characters which have special meanings in most programming languages in your labels. If you guys had frankly called that Wookiee, Ewok, and Jar Jar, I probably would have been like, yeah, whatever, okay, fine.
Yeah, it's John Graham. I'm actually an author, one of the authors on Composite Chem. Thank you again for coming to an agreement. I know it was lots of work on these things, and that, yeah, so I just learned about this registry thing too. So we will do that because it makes sense so that we don't collide with other people in the future. And yeah, it's all great. So thank you for helping us come to an agreement.
and Richard Barnes again, since we're talking about the IANA thing, like you don't even need to put something in the draft. Technically, it's a first come, first serve registry, just like email IANA. It's not a big deal.
Yeah.
Oh, so it's not, this is a full open registry with no approved or it's
Yeah,
like,
I mean,
not like
it's
TLS?
strings. It's not a limited value space. So like, you know, I don't know, someone go register all the 1-digit values if you want. But yeah, the idea was it's strings, so it's not bounded. So do your thing.
Is there a risk of not, of this growing too much if you don't have a recommended column to distinguish between things that?
No, there isn't. Like,
Okay.
No.
So I think that answers my question, which was going to be because the LAMPS draft is further ahead than the CFRG draft. Should the registry be in the LAMPS draft instead of CFRG? But if it's just a registry that we can throw stuff into, then maybe not.
Can that happen in a IRTF registry from a working group document?
Yes, yeah, you could have IANA actions
Oh,
in
okay.
an IRTF draft. Creating the table is kind of the bigger IRTF ask that is rarely done, but yeah, most of the things like Argonne 2, for example, don't have anything defined in the CFRG drafts with regard to IANA registries. It's usually when the working group includes the point for interoperability that it gets added.
Tim?
I mean, you guys are the authors. Would you do you prefer having it in your draft, or is it okay to have it in the LAMPS draft? Or
Since it references like KDF, PRG, the specific frameworks that we are trying to encode there as well, I think it makes more sense to have it in the generic draft, because otherwise it's sort of like you're registering a thing and you're like, what are these names? I don't really understand them if you're in the composite chems draft.
No, if you guys think the IRTF draft is the right place to do it, then I agree. I just want you guys to put it somewhere and for it to stop changing. So thank you.
Cool. Okay. We have no further changes that we are aware that anyone wants, that we want, that we think, no further changes. The only thing that we can think of is literally when we publish our proofs for the, RSA inspired construction and the you don't actually have to make a DH chem construction on like ePrint or something. We just put the URL in the generic draft and that's it. And then last call, etc.
So we are going to reach out to the crypto panel now before you guys are done in order to solicit volunteers because we know this is an important review.
Yeah, I just want to say to the room, now is your time.
Yes.
If no one stands up here or if there's not some immediate feedback, we're going to consider this fixed and we're going to start building other stuff on top of it and shipping while we're working out the proofs and getting things through crypto. It's not impossible. It's something will jump out of crypto review that I think we're pretty confident it won't. So yeah, get up now if you have any concerns here, anything you think might need to be changed and what might need to pause on building this.
And I'll note that the generics document, I think we're pretty done. The concrete document is not the end all be all of hybrid constructions out of wherever. Anyone can come up with their own, I'm not going to speak this into being, but a weird curve that starts with brain and a weird chem or whatever that starts with another name. You can write up that document and say I would like to register another hybrid chem construction using one of these generic frameworks. So if your favorite combination is not in the concrete document, that's not the end. You can just write that up yourself. Daniel?
One more thing on the INA registry is that for LAMPS, we don't specify a PRG because we're not doing all that fancy stuff.
Yeah.
So as long as it's okay for us to leave it blank or say not applicable or something, or even for the things that you're registering our PRG, we're using it without the PRG. So as long as there's something in there that gives us wiggle room.
Yes, we'll double check, but since we explicitly say the concrete instances may just skip this PRG needing keygen period, I think that's allowable. Richard?
I'm okay with that, but that said, it might be nice to define a PRG just because there are some security benefits to shared key generation if it ever makes sense in any deployment.
Yeah. Yeah, that's a good one.
So one suggestion for the group and folks watching is that if you are an implementer or want to be an implementer and want to take a look at these drafts with fresh eyes and try to implement it and have feedback in terms of whether certain text fits better in concrete or generic. The folks who've been working on this have been staring at it so long that it's hard to see it from fresh eyes. So please implement this. I mean, this is something that is going to be used in, as we heard, almost everything across the IETF and beyond. So the more implementations and the more feedback on how easy it is for implementers, the better.
Cool. That's it. Any random questions, feedback? Not literally. Cool. Thank you.
All right, ends early. That was great. Simon Josephson.
Hello, can you hear me?
We're sorting out the slides. We can hear you.
One moment. Oh, yeah, right. Okay, fine. Simon, do you want to be in charge of the slides?
Happy if you can do it if I just say next slide.
That's fine. Fine.
And I don't have to learn the Meet Echo stuff.
That's fine.
Okay, so thanks for inviting this talk. About the name, it seems like Star Wars is like spam in the CFRG, and it's only a little bit of Star Wars in this presentation. You have to figure it out yourself. So next slide, please. So motivation for doing hybrid signatures helps to step back a bit and see that signed artifacts have a very long lifetime, stay around for a long time, and we want to verify them later. And as you know, current signature schemes are vulnerable, and I'm arguing, and of course this is something that there are different opinions on, but I think we should consider risks when migrating to new signature schemes, and all of the newly proposed one, forgot about on here, but it's included too, is that migrating to them come with some risks. MLDSA, you have the lattices that you have to trust. For SLH, with a good, more hash-based design, you still have implementation bugs to worry about. For XMSs and LMS, there's quite complex implementation and the state handling, and hedging these by combining it with a traditional signature scheme may lower the risk in certain environments. So that's the kind of motivation for considering this at all. Next slide, please. Motivation for this particular design is combining two kind of opposite properties, and but I think the having a generic scheme that can analyze from a generic point of view, regardless of signature schemes involved, allows people to gain trust in it and not have to review several different frameworks and themselves of security of them and pick one framework. And the proposal here is just to do one generic all-encompassing scheme. And the problem with the generic construct is that engineers hate it and want to have just one algorithm that outputs what you want to actually use. So that's why you instantiate the generic framework with named instances for common and well-selected constructs. And I think this is over the last months or years become a nice pattern on how to design hybrid post-quantum stuff generally. And this is inspired by the Champat hybrid chem approach and some other patterns as well. Next slide, please. So this is just echoing Daniel Bernstein's CFRG mailing list post from many months ago. The signature this is doing not a concatenation signature, but two sequential, an inner one and an outer one. And the details are explained in the draft, and this is still a fairly early work. There are lots of details that could be fleshed out more. But I think the idea is to draft something for discussion and see if that has properties that people are interested in, and compare it with other works to get discussion. I should say that this hard coding the functions to be SHA-3. This could be moved into the instantiated algorithms rather than being hard coded in the generic design, although that opens up for questions about which properties you actually need from hash here. I think it would be unfortunate to look at older hash functions like SHA-2 here. There's opportunity to do something modern. Next slide, please. And verification, this could also be fleshed out more in detail, and in particular, since this is an inner and outer construct, this could be fleshed out to do the outer post-quantum verification first, and only after being verified do the inner traditional verification. This was pointed out recently that one aspect of vulnerabilities in implementation is that you're feeding the verification function with malicious data, and if you can protect or protect one of the implementations from receiving that data, you have gained some advantage. So there's one aspect that you react reject the message before both are verified. Details can be fleshed out more in detail in future. Next slide.
Sorry.
Right. took up time to load. It's a fair question to compare this with other work, and this could also be fleshed out more in detail. But I think the high-level point of view is that this gives you better signature properties of the hybrid than doing concatenated variants. So the point is that the combined MOPMA construct should be SUF secure if the outer post-quantum signature scheme is SUF secure. If the outer post-quantum algorithm is broken, then we have other issues too. Then we should migrate to another algorithm rather than consider the follow-on issues. Comparing it was a fair question to compare it with the LAMP stuff. That's further ahead. My understanding is that this is specific to MLDS8. It's not a generic construct. And you don't get the SUF property because it relies on concatenated signatures. I think that's at least two high-level differences. One advantage is that MOPMA is compatible with the signed message API, which is a design pattern that's known to be more robust against implementations errors compared to the traditional two separate design where you have a signature and you have a message. This is not widely adopted, but I believe it's a strong feature of the protocol that's not available in the LAPS scheme as well. There's also a question really if anyone is interested in message recovery of signatures. It's possible to describe that, but I'm not sure if there are any IETF protocols needing that. So that's a question really. Next slide. And this is a high-level comment that yes, it will be possible to find problems with this where this scheme is not optimal. And I think finding a hybrid signature scheme that offers SUF security with even if the post-quantum signature is not offering SUF, but the traditional one is offering SUF, I think that's an open research problem. And I think we should consider that the big problem is we want to protect rolling out post-quantum safe signatures without risking disaster. That's the main motivation for this, and not let the desire to reach a perfect solution stand in the way of doing incremental improvements. So I think this helps keep in mind if we find an environment where this is not applicable. I think that was the final slide.
Yep.
Happy to take discussions.
Hello, hi, it's John Gray from Entrust, author of the LAMPS Composite Signatures Draft. Could you go back to the previous slide? Yeah, so in our so it took about 6 years we worked on composite signatures. So the reason it's not generic is because that was what the original version was, and many iterations, many iterations, 26 iterations, I think in total, came to what it was based on yeah, all that discussion. Is it possible there could be other constructions in the future? Like with the FNDSA, sure, we can do that. So there's that. Yeah, the bullet about being compatible with signed message APIs. So the LAMPS draft, I guess you can think of it that way. I tend not to. I think it should be a single opaque algorithm. Of course, if someone wants to implement it with that idea in mind, they can. But again, it does fit perfectly into the existing signature APIs. And yeah, and I guess this has that, I think your construction, the second signature contains the first signature. So in terms of performance, like you won't be able to do that parallel, like both operations at once. So there'll be some operation there. And then I guess the bigger thing is like we just got OIDs assigned in composite signatures and LAMPS, right? So it's basically done. It's an IESG publication queue. So do we need more? Like I guess that's the biggest thing, because we already have 18 combinations there, and this would add, I guess, an infinite number more. I don't know. So it's a lot, right? So yeah, that's my comment.
Yeah, I agree. It's a bigger discussion to. I think this has wider applicability than just X59 or certs, but it's a big discussion.
Okay.
And fair comment.
Yeah, I mean, yeah, the way we ended up in LAMPS, I think we did come to CFRG at first, like 6 years ago, and then we went back and forth in a few places, ended up in LAMPS. So it is meant to be usable. There's other working groups that do want to use the composite signature construction that we have. So, but you're right. I mean, if there's something where this, has a very good place to use, I'm not against doing that. It's just, we have this other one and it's close. Well, basically is there. So why don't we just keep doing that?
So thanks for bringing this work. I think personally, there's still a good amount of research to do on this problem, and it's interesting to hear new ideas. Quick clarifying question. You said if MOTHMA is strongly unforgeable, if MLDSA is strongly unforgeable. What about if MLDSA is broken? If the traditional one is strongly unforgeable, is that sufficient?
No, I think that's an open research question to.
That would be a nice property to have.
Yes, I agree.
Okay. The second question, this is not directly for you. I think this is for the room. I think we need to figure out, because strong unforgeability, hybrid strong unforgeability seems like it's going to be hard. We need to figure out if IETF has use cases for it. So existential unforgeability is sufficient for TLS, for example. Are there protocols that we have that are strongly unforgeable? I think we need to have a bigger discussion about that. And then just lastly, on your question about message recovery, I don't think it's an important thing to add to this. Thank you very much.
Thank you.
Okay, Scott Fluer. As for PQ, the LAMPS proposal, all the parameter sets currently defined are listed, used MLDSA because that's the main post-quantum signature algorithm. You could define other ones for FNDSA, for other ones internally, and I expect people will eventually. But my one point is, if you go to the very last slide, your last point is don't let perfect stand in the way of progress. There's the LAMPS proposal, which is an IESG. It may say it's not perfect, but it's out there. Anything you do right here will not be an RSC for like 3 years. Are you saying that we should let the perfect stand in the way of progress? Thank you.
Dennis Jackson, Mozilla. I think, as kind of Chris alluded to, if you care about strong unforgeability, but you're worried about the post-quantum thing, so you want to do a hybrid, but you're only getting strong unforgeability, if the PQ thing is fine, It's not clear to me what you're getting from that, and I think that would be my biggest concern here. So I don't know that the juice is really worth the squeeze in this direction over just the simple thing.
Yeah, maybe that should be clarified. I think what you're getting is the hedging. If there is a fatal break, then you're getting the traditional protection. You're not getting the SUF protection necessarily, but you get some protection. That's the it's a compromise.
Isn't that the same as concatenation, though? Or like what?
Yeah,
what
if the post-quantum breaks, right? Yeah. But I'd argue if MLDSA breaks, we have larger problems.
Okay. Guilin, yeah, from Huawei Singapore. So first I would like to reply the comments from Chris just giving. So about the necessary of a strong security signature scheme or hybrid one. So actually, in the last maybe 2 or 3 weeks, there's quite a lot of discussion, but not in CFRG mailing list. In the which one? I think COSE, JOSE, and also maybe PQUIP. Yeah, there is some discussion, especially like John Madison proposed a number of the potential application scenario. In that case, maybe strong unforgeable digital signature or hybrid one is preferable. So maybe later we can forward the discussion to CFRG. It's the first one. Okay, so for myself, first I would like to know about your scheme. Do you have any kind of a formal proof analysis or plan to show your scheme, does it secure according to your claim?
Yeah. To make it perfectly clear, this is not my scheme. It's the JB's scheme, but I think having security proofs is a welcome contribution. So.
Okay, I see. Okay, the second one is that just the following. So Luca will give another talk. It's also about a hybrid signature scheme with strong security unforgeability. So if your draft is also targeted to strong for unforgeable signature scheme, so we need to consider maybe how to merge or something about these two drafts. Yeah, it depends on what user go. Yeah, we can discuss later maybe. Yeah, thanks.
Yes, absolutely. It's interesting that several contributions happen at the same time, so I'm happy to look at that draft too.
Right. Thank you, Simon.
Okay, Lucas.
Is he around? No, it's not that. Yes.
So yes, there will be quite a lot of similarities between this draft and the previous draft. So I will give a brief overview of this new individual draft that was published last month. So in this draft, we propose 2 new hybrid constructions, and we try to aim for a SUF-CMA security. So I will try to go quickly with this one because we have already talked about this. So the main motivation that the current several proposals at the IETF rely on hybrid signature schemes which only provide AUF-CMA security. But in some applications, you might need SUF-CMA security, for example, if you need protection against replay attacks. And so in this draft, we propose 2 hybrid signature constructions which offer SUF-CMA security under different assumptions. So I will briefly present the 2 constructions. So the first one is a black box hybrid signature scheme, which is very similar to the one which was presented by Simon in the previous talk. So the main idea is simply that the second signature is not only a signature of the message, but a concatenation of the message with the first signature. and it provides SUF-CMA security as long as the second component is SUF-CMA secure. So it's quite similar to the previous, to what we have seen in the previous talk. But differently, the second construction that we propose is a non-black box construction. So it was designed in the case that the first component is built from the Fiat-Shamir paradigm, while the second component can come from any signature scheme. So for example, you can use this construction with EDDSA as the first component and MLDSA as the second component. And so this construction relies on an identification scheme as well as a signature scheme. And compared to the naive combiner, it is more compact because the resulting signature is composed of the post-quantum signature, as well as the response from the traditional identification scheme. And the main difference is that this construction provides SUF-CMA security as long as at least one of the components is SUF-CMA secure. But of course, the drawback is that it's a non-black box construction. So you need the first component to be built from a Fiat-Shamir paradigm, and then use the underlying identification scheme. And so finally, yes, we plan in the next updates to add some details about the security and some refinements on the constructions. And our questions include if some people are interested to have such a hybrid construction in real-world applications, if there is a preference between the black box or non-black box constructions, and if there is any important gap that need to be filled. And if you want to have a look at more details and proofs of the security, then there is an e-print which was published by one of our co-authors, Jonas Janek. So you will find more details and the proofs for the non-black box construction. Thank you.
Yeah.
You
can go. Yeah, I unlocked it. Yeah. Sorry.
Since you asked, I have a very strong preference for Scott Fluor, Cisco Systems. Okay. Scott Fluor, Cisco Systems. I have a very strong preference for black box implementations. We really do not want to open up our FIPS components to do non-FIPSy things in it.
Okay, thank you.
Yeah.
No, never mind.
Each back based.
Yes. Okay.
Okay, so everyone, I'm Guiling. Yeah, so this is a joint work with a professor from Shanghai Jiao Tong University. His name is Haoyang Wang. So in this draft, yeah, we propose a new proposal called the HMAC-based key combiners for multiple keys. So this is the draft information. Yeah, the main background is that, of course, the key combiner are very important building blocks for security protocols, especially like TLS, IKEv2, and all other applications. Yeah, the main purpose is that we would like to derive a secure master key from a number of input raw keys. The raw keys could be used, derived from different ways. Yeah, so in this proposal, we actually gave two constructions called the HKCV1 and HKCV2 for two different scenarios. In the first version, we assume actually all the input keys are actually available at the same time, or we can set it in parallel. Yeah, the second one is that okay, the key may be arrival one by one gradually. In that case, we can set it in sequential. Yeah, so the very different feature probably compared with other existing solutions is that in our scheme, we have the decoupling feature. This means that we don't care how actually the key is derived via different ways, because the key could be divided by KEMs, either traditional or post or PQ KEMs, or maybe from key exchange protocols, or maybe just from PSK. All the keys can be covered. We just concern about the key. We don't concern which way you used. We also in our key derivation function, we do not require the input of the public key, the ciphertext, etc. This could be the very different from others. In this way, it also means it could be more efficient. Input for our key derivation function could be short. Okay, so here is the concrete construction. The left side is the true scheme from our proposal. The right side is currently currently 3 available or existing solutions. Actually, 2 is from standardizations. Yeah. So for our first scheme, you can say we use the HMAC twice basically. We have sort, and we just put all the input key concurrently to each other. So the first HMAC is used like a randomness extractor, get some PR key through the random key. So in that case, we can guarantee this way can get a good random number extractor. But we still need to use the second one, HMAC, such that even we can get enough entropy from the first one, apply HMAC. But in the second one, we would like to get the pseudo random key, such that the randomness could be still uniform, uniformly distributed in this way. And the last one, just to do some truncation, so that we only get the ideal length. Yeah. Second one is similar, but the difference is that the key is available one by one. In that case, we need to extract the randomness one by one. So it will be a repeated way. Yeah, and the right side, the first scheme is from ETSI. Yeah, just published in the beginning of this year. It also has 2 versions, one for sequential, one for parallel. So I do not give the detail here. The second one is from NIST, yeah, SP 800, yeah, 133 is published in 2020. So for this one, it's also quite similar to our scheme, but it just used the HMAC once. And also, as we know, for this scheme, it seems no formal proof security for the key combiner. The last one actually from Michael Oswas, but we know that, okay, it is combined with the current hybrid KEMs. Later we will check, yeah, whether any other difference there. Okay, this is a comparison, yeah, between our scheme and all the 3 available schemes for multiple key. Yeah, basically we can say, as we just mentioned, because our scheme has the decoupling feature, so it could be a little bit more efficient. But of course, you can argue, yeah, just HMAC. Even we use the compression hash function like for 20 times, and other scheme use maybe 100 times, but the difference is still not that big. Yeah. So about the security, our first scheme can be provably secure. Yeah, if the underlying hash function is called the delta almost universally. So it's a kind of a little weaker security requirement compared with collision resistance. Collision resistance is a quite standard security property for hash function. So this weak one is better. Yeah, second one is not that good. Second one, we only can get the security, yeah, in the model of the random oracle. So it is quite theoretical. Yeah. And the left side also has a formal proof security, but maybe as it's not as strong as us, especially the ETSI one. Yeah. I think that's all. Yeah, so in the future, we would like to do some comparing, especially of the hybrid KEMs. But of course, we know for the two drafts in the CFRG hybrid KEMs, it's mainly for traditional and PQ KEMs. But our one is actually for any kind of the key scheme you can use. This is the main difference, but we need to check more detail. Yeah, okay, that's it. Questions?
Bob Moskowitz. Find this very interesting, but my gut feeling is this is hard with HMAC. Why, doing it with a sponge function, doing it KMAC, it should be quite clear how to do combiners in feeding the information into a sponge incrementally. So I just kind of wonder, your focus here is on HMAC. It's very, very common. We use it in a lot of places. But I would like to see this also look at how we've done with KMAC in terms of feeding into a sponge. That's just my gut feeling of following this.
Okay, please have a look at our draft. We also have a research paper just published this year in the end of October. Maybe soon, it is actually the formal version of the paper will be available. So later I can let you know. Yeah, also, yeah, make announcement in the mailing list. Yeah, thanks for your comments. Yeah. Yeah, basically HMAC is already a good actually K extractor and derivation function, but that one is only for one key. So here actually we just would like to extend it for multiple keys. I mean 2 keys or even more than 2 keys. This is the difference. Yeah, we tried, but we don't know whether we are definitely right or not. So your comments, your review will definitely welcome. Yeah, thanks.
Okay, thanks. Now we're going to have a presentation that we were scheduled for before, but Armando has graciously come in at the end of this to give the presentation on a new topic related to DAP.
Hey, hello. Okay, so I thank you all for staying here until this very last time. So I apologize for not being able to present on Monday. Yeah, so
would you like?
Yes, please.
Would you like slide control?
Yes, please. Okay. Yeah, thank you. So, okay, this is a talk about some new results that I'm gonna show when I was investigating the proof system used in Prio. This is targets the BDAF draft that Chris already gave an update on Monday. So I think there is one motivation here to present these results. Here is just to if you see this pattern coming, so take a look on this pattern. So basically, in some papers you will see like defining polynomials in value representation, like the one that you have on the left of your screen. And then you have this pattern of interpolate the polynomial and then evaluate on some random point. So this is a pattern that you can find in several crypto schemes. And then what we have there is just if we have doing interpolation, we can use finite fields that have roots of unity, and then we can get like these complexities for interpolation and log in running the FFT an evaluation, it's like a linear time. So the idea here is, can we just evaluate the polynomial directly on the value representation? More technically, this is called the Lagrange basis. Well, yeah. So the answer is correct. Yes, we can do that, and this is like the result that I want to present today. This has been published at Latin Crypt in this year, and the nice thing is, or the new thing is, that it relies on a different polynomial basis called Polya. This is very well known in numerical analysis area, but not so much used in cryptography, and I think it is a preferred use for proof systems. So the nice thing is that it has a very similar pattern as the Horner's algorithm. It's linear. There is another option. You can use the barycentric formula, but this algorithm that I'm going to present, it doesn't require field inverses, so I think that is better. And also you can do like batch valuation, so you can get a reduced cost on the valuation of polynomials. Also, in the paper, I explained how to perform polynomial multiplication in this Lagrange basis. So all we know, like the textbook, polynomial multiplication, going to the through the fast Fourier transform, but they're making a more close analysis. I come up with two other techniques that I call Stolom and Rhizome. So you can check on the paper the exact details. So basically, the application for PRIO, in PRIO, we are trying to do private aggregation of measurements, and there is a fully linear proof system that makes that these measurements are like in range, or there are valid measurements. So, and this is a pattern that arises on this scheme. So basically, you have some polynomials that you define like on nodes and values, and then you have to do the verifier in this case has to interpolate and make the evaluation of the polynomials. So you can just remove like this kind of complexity, the interpolate plus evaluation, just evaluating straightforward on the Lagrange basis. So this triggers like two changes to the BDAF draft that Chris already mentioned on Monday, and then you can follow. What else? So what is the impact of that? So here you can, if you zoom in the graph, you can see like verification. In this case, it runs twice as fast, while the prover is also sped up in like 35%. Yeah, I have more slides coming up, so you can check it. But yeah, I think I'm gonna stop here in case there are more questions.
It says Q disabled on my device, but I'll just go ahead. Tim Gagan, ISRG. I just wanted to thank you for this work. This is going to speed up our PRIO deployment significantly and save us a whole bunch of money. And also, I just noticed your previous slide. I hadn't actually realized there's such significant savings for the client. That rocks, because the client is a lot of people's phones. So, saving energy, saving their battery life, like this is great. Thank you very much for doing this work.
Thank you.
So yeah, I mean, I think it's cool too. The key insight I just want to share with everybody that I had from this paper is like there's a lot, we do NTTs in a lot of things. We do NTTs in MLChem, we do them in fully linear proof systems like this. There's a lot of different things that, like that have not touched CFRG yet in the cryptographic literature that does this kind of thing. And the insight I think in this paper is like, you might think that like to do the computation you want to do, you got to convert back to have a polynomial instead of being like in the NTT domain. But they're both just bases for the same thing. They're just different ways of representation, the same thing. So before you do your inverse NTT to go back to a polynomial, think about what it is you actually want to do with that thing. And maybe there's a faster way to do there. So yeah, math is cool, that's all.
Yeah, something just to complement what Chris just said is that yeah, there are many other polynomial representation that actually are used in numerical analysis, but they have this problem about like working with real numbers or complex numbers, and they used to like find algorithms that look for that avoid the loss of precision. But for us in crypto, we do everything on a finite field. So basically, we don't have like these roundup errors or loss of precision. So I think that is good to explore what's going on other areas. And this is basically a summary of the paper. So you can see the slides with more time, and then yeah, you let me know if you have more questions. Happy to answer. Thank you.
All right. Thank you, Armando, and thanks everybody for a successful second session of CFRG. Take care.
Yeah. So if you sent it to the list, it's already done. Yeah, it just takes the transcripts and then runs it through AI tools to get. So I can take a look at that. Yeah, lately, yeah. For the transcript to see if it. Yes, yeah, it's going to.